TTP final project. Most of the material that I'm going to show here is actually already available on Canvas. So in the files, the final project, you're able to see information about the final project. So this is an applied data analysis class. So really, we want this this project to be an opportunity to apply what you've learned. And one of the best ways that I found doing that is to literally supplement kind of your ongoing research efforts. Not everyone does data analysis in their research, but I think a large portion of folks do. And so, yeah, we want to encourage you guys to apply some of the tools and skills that you're learning from this class to research that you guys may currently be doing. Oh no, all of these dates are wrong. Okay, hang on 1 second. So I have, let me pull up the correct ones over here. Okay, so this file is available already on Canvas. So while I fix this, you can see the dates for the project proposal, the project presentation, and the project report when each of these things are due. So, okay. Which are these dates? Rubric is available. That's actually the document that I just showed. So the different components of the project, what data will you be using for the project, size of the data set, source, summary of the table, what hypotheses do you want to test. Pretty standard stuff. There's a little bit more info in the rubric in terms of expectations on the content of the proposal. Really, the proposal is meant as a starting point for you guys so that you are starting to think about and starting to work on your final project. It is not expected necessarily that your work is going to be set in stone. You might change your idea later on, and that's totally fine. But I do want folks to start thinking actively about what they might do for their project. I will say that one of the unavoidable aspects of the class is that the material that we're learning is progressive throughout the class, and so we may not get to certain topics that you might want to employ until later on, and that's just by nature a limitation of the class. But you are definitely welcome to even think about or propose ideas on maybe methods and tools that we will be covering later on in the class. The last week of class, so the week before finals week, we will have project presentations. So thinking 10 to 15 minute presentations. Given the size of this class, we may not be able to do everyone, unfortunately. And so this year we will have some set people presenting in class, and then some people will have to submit recorded presentations. And we will figure that out. You can, at some point, maybe you can let me know if you have a preference for one or the other. Otherwise, we'll do a random choice. Okay? And then the project report is due at the end of finals week, essentially. And here's some things to think about. But again, there's more detail on questions and content and how the report will be graded in the rubric online. Okay? Any questions about projects? Great. Everyone's got it 100%. We all know what to do. Perfect. Okay, so let me close out of these guys. Okay, so as I mentioned at the end of class last time, we are not able to get through everything, and so we are going to pick up where we left off in terms of thinking about model interpretation, especially as it pertains to some of the topics we talked about last time with the log level stuff and with the dummy and categorical variables. So, just to kind of rehash, we are loading in a data set of wages. This is a data set that is available for you guys on Canvas in the Lecture 5 files. Looking at that again. So the structure of the data looks something like this. So we have a column of earnings, a column of the height of the individual, the gender, race, the years of education that they've had, and the age of the individual. Okay. So we ran a regression. So where we regress earnings on education, age, and then we had a factor variable, right? And so the factor is the categorical variable, and the factor is the data type that helps you deal with this, right? And the reason why we have it as a factor is if you entered it as a character, you would be trying to solve a matrix that was like 16 years of education, you know, plus 50 years of age plus male, which like mathematically doesn't mean anything, right? And so we have to translate categorical variables, and what's happening behind the scenes is that it is creating dummy variables for each category so that you have ones and zeros representing specific values of your categorical variable, okay? Let's take a look at the regression results again. So, recall that for our continuous variables, the slopes represent the sort of marginal effect of changes in each of your explanatory variable, right? So education, 4,469, the way we interpret this is we say, for each additional year of education, we see a corresponding increase of $4,469 in your earnings, right? And you know, this is where some of the intuition and interpretation of coefficients is important, right? And so would we expect your wages to go up or down if you have more years of education? Up, yeah, and so this is a positive, it's going up, and so, you know, that falls kind of in line with our intuition. Same for age, right? Age, you have 281, so for each additional year older you are, you get average earnings of $281 more, right? And again, I think that follows the intuition, right? The older you are, it's more likely that you have a higher income. You know, even if it's something as simple as like, if you have a baseline salary and they're like adjusting for inflation, no, actually that's not a good example because that would be uniform across the board. But okay, older people typically have higher income, and you see that reflected here. Yes?
I just want to ask, so when we look at the actual code itself,
Okay.
So we can by just simply using a factor, then for whatever variable it is, that will create the dummy variable.
Yep, behind the
Okay.
scenes it's creating the dummy variables.
And that'll work for any, it doesn't just have to be binomial, it can be,
Binary.
Binary.
Yes.
It can be,
That is correct,
Okay.
yes. And in fact, I can do that, right? So, wage dot model dot race, LM earnings on race. Okay, so I can do unique wages dollar race to see the different levels of race in the data set. So we have white, other, Hispanic, and black. So in this case, we have 4 different categories in this variable, and if I run this wage model race, and then I do a summary, you can see that all of those factors show up. Almost all the factors. Which factor got dropped?
black.
Yeah. And again, it's alphabetical, right? In this case, black was dropped. In the male one, female was dropped because F comes before M. And what this is showing, so okay, we can start with this one, right? So maybe this is a little bit simpler because we're only dealing with the categorical variable. It is dropping 1 because your intercept acts as the baseline for that, okay? And so the way that I would describe this is, in this data set, if your race is black, then the baseline salary is 28,372. Okay, and if you are one of these other categories, the way that we would do this interpretation is if you are of Hispanic race, then you would take the difference between this and the baseline to get the average effect of being Hispanic. So this would be 2,000, okay, I don't want to do the math in my head right now. 28372 minus 2887. So this would mean that, if you're Hispanic, the average wages that we see in this data set are 25,485, okay? So these describe the differences from the baseline, and then the absolute value is the sum of the baseline plus the coefficient that you were looking at. Okay? Questions? Yes?
We had other variable, for example, gender,
Uh-huh.
and the baseline would still be the intercept, right?
Yes. Okay. Good question. Let's look at that. Race. I'm gonna do RG for race and gender. Wait, it was vector sex. Oh my god, what did I do? Okay. Yeah, slightly more complicated. So we have 3 races and then 1 race left out, and then we have 1 gender and 1 gender left out. So, who can tell me So if you are black and female, what is the average earnings that you would expect?
The intercept value?
The intercept value, exactly, 24, 22. Okay? What if you are a other race and you are male?
The male and adding that to the intercept?
That's right. So it would be 2422 plus 3595 plus 21777. So that would be plus 3595 plus 21777. So if you are a male other race, then your average earnings would be 45,794. So what makes a bigger difference if your gender or your race when it comes to income, according to this data? Gender. Yeah, so the size of this is a lot larger than these, and so that's one way that you can do this. This data set's also really old, so it's probably, the discrepancy's still there, but maybe not quite as large as in what we're seeing in this data set. Okay, so I have a question for you guys. These values here, if I look at the standard errors, they're like not really statistically significant. So help me interpret that. Does that mean, right, so recall what statistical significance means, right? It is about the probability that the effect is real and and a probability, right, that it's like greater than 0 if it's positive or less than 0 if it's negative. So this value is not statistically significant. So does that mean that if you are someone of an other race, that your income is not statistically different from 0? What do you guys think?
Can you repeat the question?
Yeah. So we know what statistical significance is, hopefully at this point. This value is not statistically significant, which describes, right, this effect of the other race. So my question to you guys is, if you are race other, would your income not be statistically different from 0? What do you guys think? Who says yes? Who says no? Okay, I saw a bunch of people. Okay, yes, good job. That doesn't mean that you are different from 0, the overall average is different from 0. It means that if this, let's say that this value was 0, what would the average income be for someone of race other?
Depend on the gender.
Okay, yes, if they're female. If this value is 0?
24.
Yes, exactly, 2422. So even if this value is 0, it doesn't mean that their entire income is 0. You still have the baseline, right? That's always getting added. Baseline means you add it to everything. Okay? So statistical significance as it relates to categorical variables are always in reference to the marginal effect, but the overall effect always still adds this, okay? And we know with very high certainty, right, this value is very statistically significant, so it's not as though these guys will all be 0. Okay? Does that make sense? Any confusions? Yes? Yes. So, all we're saying is that when you're dealing with statistical significance for categorical variables, that is describing the marginal effect of that variable, but not the overall. And the overall, you always add the baseline. So this being not statistically significant means, so the actual interpretation would actually be, if this were not statistically significant, which it's not, then we are saying people of the other race have incomes that do not differ significantly from people of your baseline, which is if you are black. Okay? And so, in fact, we can see that if you're black, if you're Hispanic, or if you're other, there's no statistical significance in these ones. So actually, the income differences between those 3 races are likely not, I shouldn't say likely, they are not statistically significant. But I guess if you are white, it is significant to the 10% level. Okay. So, any questions about that? Yes?
So if we interpret scan over, can we say like this? Like if a person is black and female,
Yes?
the race doesn't matter, only the gender matter.
No. The race does matter because the race determines where you are. The race determines if you're here, or if you're here, or here, and the gender determines if you're here or here.
Right. Even if we have a coefficient, but then it's not meaningfully influenced to the earning, right?
It's not
It's not meaningfully influenced to the earning because it's not statistically significant. Doesn't that mean that we can do more?
Oh. Yeah, I see what you're saying. I would not necessarily interpret it that way because, you know, these values still kind of are what they are. I would, you know, you can describe it qualitatively by saying that the race is not, that the differences between certain races are not statistically significant. But even to say like, black doesn't matter, but it does in the case of like white, right? So you can't dismiss race entirely. Yeah. I saw a couple other hands, yeah.
Does this assume all the variables are independent of each other, or there's no?
Yeah, we'll get to that actually, yes.
And what might be causing the insignificance?
Oh, that's just, you know, observed in the data, right? They're like, there's enough variation that we don't have enough certainty to say that that the values are statistically different, even if on average they might be slightly higher, right? It's kind of like, well, the probability of me, you know, picking a value to be, you know, different from these things in like new data might be like, it may be, statistically it's saying that there's a large chance that there's like a, let me see if I can get this right, chance that's above 0, so this would say, if I were to randomly pick data, controlling for the other things in the model, you'd have a 55% chance of this being, okay, that's not quite the quite correct interpretation, but there's a large chance that it could actually be below this value. Okay. Any other questions? Let me see here. So if I were to let me jump over to the notepad. And try and reiterate this from a graphical perspective so we can kind of get an understanding, an additional way of thinking about this. Okay. So let's take an example. Earnings is equal to beta 1 gender. Right, so the way that I would view this kind of graphically, I actually don't really have an x-axis in this case, but so wage or earnings, the idea is that you actually have two lines whenever you have a dummy or categorical variable representing essentially multiple lines. And this would look something like this: male and female. If the intercept was 21,000, and then this delta is the coefficient for male, which is 20,000. So then the actual value for male would be like 41,000, something like that. Okay? Does everyone understand this plot? Yes. Great. Now, if we go back to our simple example of linear regression for what we've been doing so far, and we just did one variable, continuous variable, and that would be something like this. Beta, let's do beta times education. Okay? So this one should be easier to interpret. So education and wage, right? And we have a line that looks like this. And that line is the beta coefficient of our education variable. And that describes for every additional year of education, this slope is telling me that I get, what was it, like $2,800 increase in wage, something like that, right? And so this, every additional year of education that I get, I'll have higher wage, higher wage, higher wage, and that's related to the slope, which is the coefficient value. Okay? Questions about that? Yes?
For the graph on the left, you said there's no intercept, but wouldn't the intercept be the value of female?
Yeah, I meant that there isn't this axis, the bottom, the x-axis isn't really a thing, yeah. But I'm drawing it this way, for the purposes of the next ones that I'm drawing. And in fact, if you wanted to kind of think about it, if you had a model that just described gender, the axis for this could be education, and what it's saying is that education, because I haven't added it into the model, doesn't make a difference in the wages. It's not in the model. But what if it were in the model? So what if I did earnings is equal to beta 1 gender plus beta 2 education. Oh, sorry. Does anyone want to guess what the plot will look like? Yes.
Look like the one above it, but where the lines are slanted.
Yes, exactly. I will have two parallel lines here and here. Okay, and this one will be, bottom one will be female, top one will be male. What is the value of the slope? Beta 1 or beta 2. So both of these, in fact, let me color code it. So slope equals beta 2. Okay? And what would for any given set value of education, what would the difference be between male and female?
Beta 1.
Yes, exactly. So this difference is equal to beta 1. And in fact, if I had an intercept plus alpha, that would be this thing, and then this value here would be beta 1 plus alpha. Make sense? We're building up our intuition. So this is saying, right, if you are male, you make beta 1 more money than if you are female, no matter where you are, and both males and females will benefit from having more years of education, and both males and females will have a beta 2 increase in their income for every additional year of education that they have. Okay, can anyone guess what the next step is? So, what if we wanted to see if years of education affect your gender or are affected by your gender differently? Okay. Like visually, what would that look like? What do you guys think? Yes.
The slopes of the two lines be different.
Yeah, exactly, right? And so if this were steeper or more shallow, or if male was steeper or more shallow relative to the other one, that would then mean, right, for every additional year of education, that the increase in income for a female would be different from the increase in income for a male. So that might look something like this. So education, wage, and we would have maybe something like this. Male, female. And the equation for this would be beta 1 gender plus beta 2 education plus beta 3 the interaction between our gender and education. So you can imagine the gender is 1 and 0, right? 1 for, let's say, male and 0 for female. So if you're female, you have 0, and then this term falls away to 0, right? And so then the equation for female would just be this, right? And your education slope would be describing that. But actually, if you are male, this becomes a 1, and you have an additional beta 3 term. So what, okay, so if the slope, of female is beta 2, what would the slope of male be? Anybody? Any guesses? Yes? It would actually be beta 2 plus beta 3. And so, okay. So remember, so this is beta 2 plus beta 3. Yes. So there is a difference in the intercept, and that's where beta 1 comes in. But the beta 2 for education does not go away, you know, if you are looking at male. It's actually additive to this. So the slope is now beta 2 plus beta 3 for this. And then let's say we have our intercept. So our interpretation here, this intercept would be here, and then same as before, this is equal to this plus this, so this is beta 1 plus alpha, and this is, this is just alpha. Okay, so it's going to be a little bit tricky to interpret correctly. It takes a little bit of practice, especially if you're seeing this for the first time, but really make sure that you can nail down this understanding, okay? So we're building up, right, dummy variables, they're just 2 different intercepts. Continuous variable is just a slope. When you have both of them, you will have multiple lines that have the same slope. The slopes are described by the continuous variable, and the intercepts are described by your intercept and your dummy. And then when we have combinations where you have interaction effects, your slopes are described by the continuous variables plus the interaction, and then your intercepts are the same as before, still with your intercept and your categorical variable. Okay? Yeah, there's going to be some questions in homework 2 on this, so it'll give a little bit more practice to kind of help sort this out. But being able to interpret this is very important because, you know, you're gonna be dealing, it's very common in lots of data sets to be dealing with discrete variables and continuous variables and kind of figuring out what they mean in terms of interpreting them relative to the outputs. Okay, any questions? Oh, this thing's out of batteries. Yes.
I was gonna ask, like, generally in models, like for this one, the last one that was specified, there is a term for education, and then there's an interaction term for both gender education. When it comes to best practice, is it usually just one or the other, or is it, do you usually put in both?
You're asking about when would I do interaction variables, essentially?
Yeah.
Okay, good question. So, actually next week, Yanning is gonna talk to you guys about what's known as subset selection. In other words, how do I know what variables to put into the model? And there are actually specific techniques that we can employ in order to determine whether it makes sense for certain variables to be in a model. And that can be a pretty nice guide for figuring this stuff out. That having been said, most of the techniques that Yanning's going to cover next week may not necessarily help you specifically with interaction variables. Okay, so here is why interaction variables are typically thought of as something that you insert into a model more based off of a qualitative understanding rather than a quantitative understanding of, or trying to quantitatively determine this. Okay, let's suppose that we have you've got a data set with two variables, and you're like, okay, I want to see if it makes sense to put x1 or x2 into the model, right? And so you can systematically test this. So we can do y is equal to beta x1, we can do y equals beta x2, or we can do y equals beta x1 plus beta x2, okay? And we can evaluate these different models in a variety of ways, using some of the metrics that we've already talked about, and then some metrics that you guys are gonna learn about next week. We can figure out, okay, turns out, you know, okay, okay, hang on. So we're gonna cover a topic in just a moment, actually, that's gonna be related to this, but technically, the more variables that you add into the model, your model will always perform better on the data that you train on. But it may not necessarily be the best model. And I'm not gonna explain that exactly why right now, take my word for it, but it could be that like this one is the best model. Okay, when I have x1, x2, how many models am I testing? 3. Okay. What about if I have y, x1, x2, x3? Okay, so now I can test y equals beta x1, y equals beta x2, y equals beta x3, y equals beta x1 plus beta x2, y equals beta x1 plus beta x3, y equals beta x2 plus beta x3, and then y equals beta x1 plus beta x2 plus beta x3. Okay, how many models do I test out of here? So this is 3, 7. Okay. I'm not going to do y, x1, x2, x3, x4. So this complexity, or the number of possible models to test, increases by a general order of 2 to the n, where n is the number of variables. Okay, so one of the reasons why we're going to talk about strategic tools next week is because you don't want to be testing this many things. Okay, it gets way too computationally complex very, very quickly. Okay, especially these days we're talking about like machine learning and doing like 10,000 variables, like 2 to the 10,000. No way, no computer in the world will be able to suss through all of that. So we have shortcut techniques to do this. Okay, getting back to your question. Well, what about interaction variables? How many interaction combinations are there here, right? So you actually will increase at a rate exponential to 2 to the n. So our ability to test all the interaction possibilities is an even harder problem. So our ability to say, oh, I should do this interaction and not this interaction, but I should do this interaction and not this interaction. If we were to comprehensively, quantitatively test that, it would be impossible. And that's why we say you include interactions if you can come up with like a qualitative reason why we think that would make sense, right? So do I willy-nilly put in wage times gender as an interaction term? No, I'm only doing that because I suspect that the education outcome effect is different between genders, right? So if you have some hypothesis about that, you can test it, but you wouldn't be able to, go try every interaction, unfortunately. Does that help? Okay. Questions about this? Okay, let's move on. To our main topic of the day. So this is going to relate to this idea that I just said about, this model here is technically the best model for if we're considering like metrics like r squared, or if you're looking at the lowest mean squared error, right? And why is it that this is strictly better than this? Well, if you think about it, this model kind of subsumes this model, right? This is a subset of this, because at the very least, I could just set this beta to be 0, and then I would capture the same thing, right? So strictly speaking, this is going to be always a better model when we think about r squared, when we think about mean squared error, when we look at the overall residuals. More model complexity, aka the more variables we add to the model, you're always going to perform better. So, let's see here. If I have some data, and I draw a line through it like this, okay, so we can create a better fit by adding more explanatory variables. Okay, sorry, I need to check something very quickly. Sorry. Yes, okay. Okay, back to here. So one of the ways that I like to give an example of this is you can do something like this. Y is equal to beta 1x, and I can actually add flexibility into my line by adding more explanatory variables. And I can generate that actually right off of my x. I could do something like this. Y equals beta 1x plus beta 2x squared, and that may let you do something like this into the line, and I can continue to add in terms like so. And the more and more terms that I add, kind of the more squiggliness that you can add into your line. You're essentially adding degrees of freedom in a way, because you're like adding in all this like extra data fit that could be helping to make the line get closer to these points. And so this is a concept that we've been kind of visiting and revisiting throughout the classes so far. And the idea that I want us to start thinking about a little bit more is we have been adding more and more complexity into the model. But think about what would happen if throughout all of this data, let's say you had a bunch of data points. What if you, instead of training the model on all of that data, we actually left some of it out, okay? And then after I train it, then maybe I start plugging some of that data back in, okay? So what happens if I plug in some of the data originally in here? So suddenly, this question of, you know, the red line being the best might not be the case, right? With the green dots, which is the data that I left out, I can look at how my different fits compare, and now suddenly it might not be the really complex one, it might be one of the intermediate ones, it might even be the simplest one, okay? So the concept that we're talking about here is overfitting, right? And so when I put in that new data and I see the fit, is it like really different? Have I actually overfit to the data that I originally trained on? And how can we try and avoid that? So it turns out that there's a fundamental property of adding complexity into the model. And so this is known as the bias variance trade-off. Okay. So the simplest way that I can describe bias and variance is something like this. So say we've got 4 targets, 4 kind of bullseye things, so you can think of this as like a dartboard. If I throw a bunch of dots, or a bunch of darts, not dots, and I bullseye all the time. So this is an example where you have low variance and low bias. If I throw a bunch of darts and I am centered in the right place, but there's a big spread, this is low bias, but high variance. If I am very accurate, or sorry, that's literally the wrong term to use. If I'm very precise, but not very accurate, this is high bias, but low variance. And then if I really suck at darts, this would be high variance, high bias. Okay, so the variance is kind of describing the spread, and the bias is kind of describing your precision, like where are you throwing generally. Okay. Any questions about this? Okay, so the bias variance trade-off comes fundamentally into your error term. Okay, so there are, I'm gonna give a little bit of mathematical formulation as a derivation thing, but it's not important to know the actual math here. So error, the components of my error, I can actually derive. Sorry, make it a little bit more clear. Error is equal to expectation y minus predicted given my x's squared. This is equal to, so there's a little bit of stats math going on here, but as I said, don't worry too much about this. E x minus okay. If you were in a traditional stats class, you might spend a lecture or some part of a lecture kind of deriving this. We're not going to do that. The important thing about this breakdown is that it actually separates our error term into 3 pieces. And that looks something like this. Bias squared plus variance plus noise. So that is this term, this term, this term. Okay, so the 3 components of error are bias, variance, and noise. So this is like the random stuff, and these guys are artifacts of how your model is performing in fitting the data. Okay? Oops. bias squared, not bias squared. So bias squared, variance, and noise. So it turns out there is a universal phenomenon that happens. Okay, so think about this. Okay, think about this in relevance to your your targets here. So as I add more and more complexity to the model, and I'm throwing the darts, essentially when I think about how close I am to the true values, so in this plot, you actually continue to decrease your bias more and more relative to your green dots, to the test set that you've left out. But as you add more complexity, you could get more squiggly and more squigglier and squigglier lines, and you might actually end up getting farther from the green points, and that's actually the variance term. So, this is the most important plot in the class, okay? So if there's one thing to take away from here, it's this. Model complexity and error, okay? So we've got the bias term here. Bias decreases as your model gets more complex. Variance increases as your model gets more complex, right? More squiggly, more variance, a part of the error for the testing. So the total error, which is the sum of these two plus the noise, looks like a parabolic curve like this. This is almost without exception, your error will look like this as a function of model complexity. Yes?
Can you describe the bias line in terms of some example? How does bias decrease under these contexts?
Yeah. So if I go to this example here, the idea is that even though your variance increases, right, like the green points relative to the red line, and as you get more and more squiggly, the squiggliness of the line is still centered around where the green points are. Right? And so if the test set is representative of kind of the average values of your training set of the black ones, then as you increase model complexity, you will get on average like closer to your bullseye, even if your variance is increasing. Does that make sense? Okay. So where do we want to be in terms of model complexity? Should we make our model super simple? Should we make it super complex? What's the best spot?
A middle point.
Yeah, right here, right? We want the lowest total error. And so a lot of the rest of this class is how to figure out how to get there. Okay? So, yeah, just to kind of reiterate, if you have looks like this versus if you have a fit that looks like this, and you have points outside here. So this is bias error, and this is our variance error. It's very kind of simplified, but yeah, this is what we're talking about. We are trying to find the middle ground between getting too much complexity and holding back on adding more variables and more complexity into the model, while trying to get decreased biases as much as possible. All right. Any additional questions about this?
On the
Uh-huh.
graph that shows the variance error, are those blue dots, like, are those part of the data set that just the model isn't capturing?
Yeah, except that it's like, it is data that has purposely been left out.
Okay.
So the idea is like, you have some data set, and if you train a model on that data set and then you try to re-predict outcomes based on data that you've already seen, it's kind of like, well, you trained on that data, so obviously you're going to do well on guessing, right? So the idea is, if I purposefully leave out data, is my model really that good at predicting things that I haven't seen?
Okay.
Yeah, and that is actually the concept for how we will get to the lowest part of the total error. Okay, any questions? This is like the most important concept for this class, so if you're confused, speak up. Okay. Let's see here. Okay, so this part, you guys don't need to follow along. I'm gonna copy and paste a big chunk of code. Alright. Okay. What the heck are we looking at? I have generated some data. So this is pull this down. Okay, right here. This is kind of similar to what we've been doing so far. So you guys can see X are uniform, 50 points between 0 and 2. So everyone can hopefully follow along there. I have my error term, deviation, same thing. And we have been doing this thing where we do y equals 0.5x plus the error. I made it a little bit more complicated. So that's y is equal to sine x times cosine 10 times x plus 0.5x plus my error term. So it's like a weird, wonky, sinusoidal thing going on. And what I've done is I have trained a set of regressions on that data, and the data that I'm training on is represented by the black dots, okay? Ignore the blue dots for a second, not relevant to this. Yeah, okay. And what I've done in the code is actually exactly what I was describing in the written notes. The top regression is y equals beta x. That's the model that I tried to assume. The next one is y equals beta x plus beta x squared. And this one is plus beta x plus beta x squared plus beta x cubed, beta x squared, beta x cubed, beta to the 4th power, and so on and so forth, okay? So what you guys start to notice is as I add more flexibility to the model, my fit line starts to get a little bit more wobbly, more and more wobbly, and there's a number displayed in each plot. And that number is the mean squared error, okay? So this is what I was saying before. Look at 1, compare that to like 17. You guys think that 17 is a better fit than 1? Yeah. And in fact, quantitatively, we know that to be the case. In fact, wait a minute. Oh, I'm already showing the out of sample one. Okay. Well, ignore this number for now. The in-sample mean squared error, that number, it will continue to decrease. It will always decrease as I go from this to more and more x terms. It will always increase because, remember, like I said, you could always set one of the betas to 0, and it would be the same as, you could theoretically have it end up matching something from before. So you will always get better mean squared errors for in-sample. But what I've actually done is I left out data. And the data that I left out are these blue dots, okay? Now I can actually recalculate my mean squared error on the blue dots, which we call an out of sample mean squared error. Out of sample because I did not train on that data. These red lines were not trained on the blue dots. And I can now recalculate my mean squared error. And what you see is the phenomenon that I drew in the plot with the bias variance, okay? My mean squared error will decrease as my bias goes down. So 0.8, 0.7, 0.5, 0.6, 0.4. It continues to decrease right up until here, 0.291. And it turns out when you do the out of sample mean squared error, like that is how you're capturing the variance error term. And eventually that variance error term catches up, right? And so remember, we've got the parabolic mean squared error, or error term, which the mean squared error is representing. And suddenly your error term starts going up, okay? See, 0.262 is the lowest, but it goes up to 0.3, 0.349. So you are starting to see overfitting happening as I add more complexity to the model. Okay, which is the best model? How many? Sorry? Yeah.
Either 12 or 13.
Yeah, exactly. You want to look for the one with the lowest out of sample mean squared error, so 12 or 13. I could probably go in and find the like decimal point at which, you know, But yeah, you're gonna be pretty similar. And so it turns out that this kind of procedure, this kind of phenomenon is, what I'm displaying here is essentially how we maximize the reduction of our bias while maximizing the reduction of our variance. And we're getting to the bottom of that overall error term. And so we avoid high bias and we avoid overfitting. Okay? Questions? Yes?
I'm confused about the out of sample mean square error. So that's only for the data that we left out,
Mm-hmm.
or
Yep. So just to be clear, right? So we train the data on the black dots. That's where the red line comes from. If I wanted to calculate an in-sample mean squared error, the procedure would be the distance from here to the red line, the distance from here to the red line, the distance from here to the red line. Each black dot, I calculate the distance to the red line, and then I square it, or I take the square of the difference and I add it up. That's the in-sample. The out-of-sample, very similar. Instead of doing the black dots, distance to the red line, I do the blue dot, distance to the red line. This minus this, this minus this, this minus this, and then I square each of the differences, add them up. That's my out-of-sample mean squared error. So all the numbers here shown are the out-of-sample mean squared error, and that is when you see your error term, parabolic error term. If I were showing the in-sample mean squared error, the number would always decrease. You wouldn't be able to tell where you're overfitting. Actually, I wonder if I can do that really quick. Did I save MSEs? MSE, I don't even see it. Text, okay, MSE, yes, okay. So, I think I can do this. Okay, all the way to the bottom. If I change this to MSE train instead of test, I think that will do it. Yes. Okay, so now the number is showing the in-sample mean squared error, and you can see it should always go down. Yep, okay. Yeah, 0.3, 0.282, going down all the way to 0.1, decreasing to 0.03, down to 0.03, 0.02, and so on. Because we're training on the data, so we don't actually know when we're overfitting. Okay. This is the, right, they're not all gonna look perfectly parabolic, but the general trend will look like this. And so this is our model complexity. As we add more exponents, the more complex the model is. And then our test MSE or our out-of-sample MSE looks like this. And right around here, excuse me, is where we said is the lowest. Okay. Yes?
Why, there's a couple points just above 5 exponents where you actually see the test MSE go up.
Yep.
Why wouldn't they just zero out some of the variables, or is it not minimizing MSE?
You're asking like why isn't the shape perfectly parabolic as opposed to like here we kind of go down and up? And
You know, like why would it go up instead of just zeroing out on the exponents to,
oh,
or one of the terms?
yes. This has to do with I see what you're asking. Yeah, why wouldn't it just do that? Oh, yeah. This is just an artifact of randomness. Remember that in the test MSE, you may not always ideally get that kind of shape. It's the in-sample MSE that it would zero out and never go down. But like coincidentally, you can have these cases where it just the test sample fit to a particular thing with the exponents is will lead to artifacts like this. One of the prominent features that one of the prominent features of models that have these like exponent terms, and I think we can see it here. Yeah, a little bit. So one of the things about having x squared, x cubed, x fourth, and so on is at the edges, you're really unstable, and so you could have a lot more wiggliness at the edges. It's like not as prominent in this particular example.
Maybe 6 or 7.
Yeah, you can see how this goes like this, and then it immediately whips around and changes the shape. So that's kind of what I'm talking about there. So you can imagine that it could just be where these blue dots kind of line up relative to the like weird stuff that happens at the edges that you may sometimes eventually get like higher error. Okay, any other questions? Okay. Alright, I'm gonna scoot this one. Yeah, so let me kind of maybe formalize a little bit this idea. Okay. All right. Let's move over. Move over. Come on. No. Oh my god. Right, let's just go down. Why is there a finite amount of space on a digital whiteboard? It makes no sense. Okay. How do we test the goodness of a model? Right, so this is what we've been talking about, out of sample validation. So the concept, which I have been trying to introduce, is we have training data and we have testing data. Training data is used to calibrate the model. And then we test the model using the calibrated model and then feeding in the testing data. And then this can continue to iterate to calibrate the model. So R squared, standard error, residuals, and MSE. These are ways that we test the model, and MSE really is going to be kind of one of the gold standards that are commonly employed, from these more simplified regression techniques all the way to very complicated machine learning models. MSE is kind of our gold standard for what we would use to figure out whether or not a model is good. Okay, so I got a big data set, and then I want to think about this concept and like how would I actually go about implementing it with the data set, right? So I know that I need some training data. I know that I probably want to have some testing data. How do I take my data set and separate it into a test data set and then a training data set, right? Is there some procedure to do this in a systematic way? And like even if I were to do it randomly, if I have this big data set and then I separate it into training and testing set, like what happens if I got all the outliers that just happen to be in the test set or happen to be in my training set? What if like I have coincidentally separated my data into bits of weird data in one and other data that looks really different in the other? Then I might have coincidentally just made it so that the test that I'm running on how good the model is ends up looking a little wonky, right? Like that could happen. So is there kind of a systematic way for us to do that? And the answer is yes, obviously. So one of the things to note is like, the other point about, so the other point that I wanted to make about training and testing data is like, you typically want to calibrate your models to as much data as possible, right? And so by leaving out some data or like carving out some data, you somehow will lose the ability to do that, right? So let's say you come out with a training set and you come out with a testing set and you're like, well, you know, it would be great if I could use that testing set to also train the model in some way, because I'm like losing some fidelity by not having the ability to run the model on that. So there's a kind of clever solution to this. There's a set of techniques called cross-validation, which allows you to do out-of-sample testing, and this is a procedure where we use our data to artificially make a test set. And the particular cross-validation technique that we're going to talk about today is known as k-fold cross-validation. So this is a procedure that employs the entirety of your data set iteratively to test the predictive ability of your model on, we'll say, quote unquote, new data. And when I say predictive ability of your model on new data, really that just means the outer sample mean squared error. Okay. Okay. So let me write out the steps of this procedure, and then we'll talk about, we'll talk qualitatively about how this works, and then I'll show an example of implementing this in the code. Okay. So, steps. 1, define K. This parameter divides your data set into roughly equal parts. So commonly used K values, K equals 5, K equals 10. And that would be known as a 5-fold cross-validation or a 10-fold cross-validation. Okay, split the data set. So randomly divide the data set into K equally sized parts. And then for each fold, and I'm saying for each fold, kind of in a pseudo-algorithmic way, much in the same way that you might use a for loop in R, you would first set aside one fold. This is the test set. Train the model on remaining data. Then validate the model using the test set. Record the performance metric. So this could be MSE, AIC, PIC, which you'll cover next week, etc. And then 4, repeat step 3 for each of the K folds. And then aggregate performance metric across all K folds. Okay. What the heck did I just describe? Alright, so let's suppose you've got a big data set. You got many columns of data, many rows of data. What you're doing here is you take that data set, and then let's give an example of a 5-fold. I'm gonna assign an index number to each row of data. So, and that index number is gonna be between 1 and 5. Row 1 gets 2. row 2 gets 3, row 3 gets 5, and so on and so forth. So now, once I've done this, every single row of data has a value associated with it. 1, 2, 3, 4, 5. Okay? Is everyone following along? Okay. So I've got my original data set. It has like a tag ID, right? 1 through 5. I say, okay, take every row that has a tag 1 with it, get it out of there. Train the data on the rest of the data, train the model on the rest of the data, which means that that model is trained on all the rows that contain an ID of 2, 3, 4, and 5. And now I have my fit line. Now take the ones that I left out and calculate the out of sample mean squared error. Okay? Is everyone following? So that is like this step 3. And then, okay, take that out of sample mean squared error, store it somewhere. We'll start again. Here's my big data set. It has all the IDs 1 through 5 randomly associated with each row. Now take out all the 2s. Train the model on the data that has IDs 1, 3, 4, 5. And then calculate the out of sample mean squared error for the 2s that was left out. Take that, store it, and then do it for taking 3 out, then do it for taking 4 out, and do it taking 5 out. And so this way, I've actually been able to technically train across all of the data across different folds, and I have avoided the problem of, in the random selection process, like if the data in 1 happened to be kind of weird, well, I've also averaged that out against the errors in when I left out 2, when I left out 3, when I left out 4, right? And now you have an average out of sample mean squared error for a particular model. Okay? So that makes sense for everyone? Right, so if you were to kind of like draw this, you have your full data set. This gets separated into your training data and this is your test data. And you would run the model on this, then calculate the out of sample mean squared error on this, put it back, take out a different chunk, run the model, run the out of sample mean squared error, put that chunk back, take out a different chunk, run the model and the training data, calculate the out of sample mean squared error, right? So this is known as k-fold. So a 5-fold means I divide the data up into 5 pieces. 10-fold means I divide it up into 10 pieces. There's a special case called leave one out cross-validation, where if you have n number of rows, you divide the data out into n folds. So you take one data point out at a time, calibrate the data, do this error of that one point, and then average it across as you run through all of the points. Okay. Questions?
Do you do this in the first place because the full data set is too large to train the model on?
No. You do this because you don't want to train, if you train the data, or if you train the model on the full data set, then where's your testing data coming from? You don't have any testing data. Okay. So, how do I do this in code? So this is an example for the wages data set. And walk through the logic of this. Well, this particular algorithm that I'm putting here, you guys are gonna get intimately familiar with. You guys are gonna code this yourself on some of the homeworks and do some interpretation of this. So it is important to really understand what's going on here, okay? So this code is just the codified version of the steps that I described qualitatively. And we can walk through this to do exactly that. Okay. So what do I need as inputs for this function? I need the data set, which is input, and I need k, which is the number of folds. Okay, so you could do 5-fold, you could do 10-fold, you can do leave one out, which would be the n row of input. Okay. Index. Sample 1 through the number of folds for n row input. What does that mean? I am going to, let's say I have a data set with 100 rows. It means that I have to pick out the number 1 through 5 100 times, right? So I will have a vector of random numbers between 1 and 5, and that vector will be 100 long. And so what are we going to do with that? If you guys can visualize, right, I'm just going to take that and attach it in as a column to my original data. So now my original data has a column called index, which is randomly assigned index numbers for 1 through the number of folds. Okay? I'm setting up an empty bin to hold my MSEs. Remember, every time I said, you calculate the out-of-sample mean squared error, put it to the side. When I say put it to the side, we're going to store it into this object. Okay? So for n in 1 to number of folds, so for each fold, I'm going to go, 1, 2, 3, 4, 5. So in 1, I'm going to take my original data input and I'm going to separate it out into training data and testing data. How do I separate out these things? Don't worry about the code, just as I explained what's happening.
You're taking a piece of the data.
Yes, and the piece that I'm taking out is determined by
N.
It's determined by the index, right? And so it's in the first step through this for loop, I'm taking out all the ones. And then in the next step, I'm going to take out all the twos. And then in the next step, I'm going to take out all the threes. So when I say take out, that's the testing set. So testing data is my original data, where the index is what I'm stepping through. So in the first loop, it's going to be 1. Okay, so testing data is original data, index equals 1, and the training data is everything else. Training data is my original data set, where the index is not equal to 1. Okay? And then I run my model, except data is not the original input, data is the training data set. Great. And now I can generate my mean squared error. The mean squared error is my predicted y values minus the actual y values. So I generate my predictions. Mean is equal to the, I'm generating predictions on the testing set, okay? And then I do y minus y hat squared. This is my out-of-sample mean squared error, and I stick it into this thing. And then I go back up here, my next fold is 2. Take the original data, everything not equal to 2 is training data. Original data, if the index is 2, that is my testing data. And I do this again and again until I get your mean squared error. This is a vector of mean squared errors, and the average of this value would be kind of your out-of-sample mean squared error of your k-fold. Okay? I know this is complicated. Take some time to digest this. We will revisit this throughout the class. Out-of-sample cross-validation is something that we are gonna do like again and again and again. So look at the notes, at least get the steps that I described kind of straight in your head. Don't worry too much about the code, you'll have practice to do this, and Yanning will visit this again next week. Yeah, I would encourage you to take some time to, make sure you understand how K-fold cross-validation works. Okay, and that's it for today. As a reminder, homeworks are due at the end of the day today for homework 1. Homework 2 will come out on Monday of next week. I unfortunately will be, as I mentioned on Monday, I will not be available on office hours or next week. I'm going out of town for a conference, and Yanni will be covering the lectures. But I'm working that whole time, so if you guys have any issues or anything, definitely feel free to still email me, and I will try my best to be responsive. I will be responsive, so